Okay, this is the final video for Chapter 11, Timers Part 2. I'm going to expand on the pulse width modulation demonstration that I did with the PIC-18 simulator. And now instead we're going to do a hardware demonstration on the actual PIC-18 4520 chip that I have installed on my board on an Explorer 8 demonstration board, which we can see in the side window there. We'll zoom in on the video and point out everything in a second. The changes we have right off the bat is this processor runs at an oscillator frequency of 8 megahertz. That's the actual hardware oscillator that's on the demonstration board. So I redid the calculations based on the fact that I wanted to make, in this case, and a frequency of 80 kilohertz. I did 80 kilohertz because that's out of the human hearing range, so that I won't get this really high-pitched whine in my ear as it's switching in and out the motor. I'll hear the motor running at different speed. But okay, so based on those calculations, I decided to set 2 fixed duty cycles, basically because of the 8 megahertz and 80 kilohertz, the math turns out to be 25 instead of 250 that goes in the period register. And then what I'll do is I'm going to use a push button switch to determine that I either set a duty cycle of 18 out of 25, which is going to be 72%, or 22 out of 25, which will be 88%. And those will give me 2 different visible motor speeds, and I'll actually see those on the pulse width modulation waveform. So remember, the waveform comes out of port C pin 2, which is CCP1. So this is where I will actually hook my motor up, and I will actually hook an oscilloscope up so we can actually look at the waveform. And as an input here, I've hooked up an actual input switch to port C pin 1 because they're right next to each other, so I can get them in and out of the processor real easily on the umbilical, with a pull up switch and then a ground, so an active low switch hooked up to port C pin 1. So my software will simply read port C pin 1. If the switch is open, I will run the motor at 72% by putting 18 in the duty cycle register. If I push the switch, then I will put 22 in the duty cycle register, and we will run at 88%, so we should get a faster motor. Now for reference, when we put this up on the oscilloscope, 80 kilohertz turns out to be a period of 12.5 microseconds. So we should be able to observe that 12.5 microsecond period on our oscilloscope. Okay, so let's switch over to the camera view now. And in the camera view, unfortunately, my mouse doesn't show up in the camera view, so I have to use my really high-tech pointer here. So here we can see the actual PIC-18F4520 chip with all its 40 pins on it. Those pins are brought over here on the side, and I can actually, if you could zoom in and read enough, you can see port C pin 1, port C pin 2, power and ground, which are then connected out this umbilical to this little mini breadboard. In this breadboard, I've got a push button switch with an actual pull-up resistor. See a little striped pull-up resistor here? So there's my pull-up resistor hooked to red, which is 5 volts. And then that is being read via the blue wire back into the processor, port C pin 1. The pulse width modulation signal is coming out the green wire here and being routed onto this piece of hardware, which is called an H-bridge. It basically is some MOSFETs that are used to switch in and out the 9-volt battery that's actually powering the motor. So notice the microcontroller is not running the motor, this 9-volt battery is. So the pulse width modulation signal switches in and out the 9 volts to my motor, and I got little white stripes painted on my wheel here, so I ought to be able to see the speed of the motor going around. The other thing I have is right here at this junction on the breadboard, I've got the orange wire here. This orange wire is being fed back into the analog discovery. So this is my oscilloscope that I'm going to put up on the screen, and I'll be able to observe the waveform, duty cycle, and period, so I can verify the frequency. Okay, I'm going to turn this processor on, and my motor starts spinning at a certain speed. Unfortunately for you, the noise canceling on my microphone is too good. You actually can't hear the motor running like I can. I wish that would have come through. So if I take my fat finger up here to go push on the button, right now I'm not pushing the button, so I've got one speed. If I push on the button, we should see the wheel is spinning faster now by the faster white marks going around in the video. If I let go of the button, I'm back to my slower speed, faster speed, slower speed. Now, if we then just take this orange wire that's coming up into the analog discovery, I can share the analog discovery up on the screen here. Hopefully we can still see the wheel going around in the corner. So here's my orange wire being graphed over here on the analog discovery. And so we can see that this waveform is on a whole lot more than it's off. If we look down here, this is 0, and out here to about 12.5 microseconds is our verified period. So we've done our calculations right and have the correct frequency. And then what I have here is I have a voltmeter right here measuring the average DC value of this waveform. And right now we're reading 3.5 volts. And so that corresponds to our 72% duty cycle and should make our motor move at the slow speed. If I then push the button, I now have a higher duty cycle. I'm at 88% duty cycle. Notice our average DC value has gone up to 4.3 volts. If I release the button, I'm back down to 72% duty cycle and 3.5 volts with the slower motor speed. So here we have a pulse width modulation demo where we can actually observe the pulse width modulation waveform coming out of port C pin 2, being graphed here on the analog discovery oscilloscope, and then actually being able to observe the motor going round and round in the window here. So I've got my two motor speeds. This is my slow motor speed, and then my faster motor speed when I push the button, which got the higher waveform speed. So let's hope this video came out good. We'll stop and test it.